On January 21, 1968, a B-52G Stratofortress approached Thule Air Base in northwest Greenland carrying 4 nuclear weapons. The mission was routine. The aircraft had been airborne for hours over the Arctic. Inside the cabin, a fire began and spread through the insulation and wiring. Smoke filled the cockpit. Systems failed. The crew attempted to control it, but could not. One by one, they abandoned the aircraft over frozen sea ice. The unmanned bomber continued forward until it struck the surface of North Star Bay. The conventional explosives in the weapons detonated on impact. Thule Air Base sat on the northwest coast of Greenland, more than 750 miles north of the Arctic Circle. The installation was built during the early years of the Cold War under agreements between the United States and the Kingdom of Denmark, which governs Greenland. Its location was not chosen for comfort or accessibility. It was chosen because it was close to the shortest route between North America and the Soviet Union. On a globe, the distance between the continental United States and western Russia shrinks when measured across the polar region. During the 1950s, American defense planners recognized that any long-range bomber or intercontinental ballistic missile launched from Soviet territory toward the United States would likely cross the Arctic. Greenland became a forward platform for detection. The base supported the Ballistic Missile Early Warning System, known as BMEWS. Large radar arrays scanned the northern sky for incoming missile trajectories. The purpose of the system was simple: detect a launch, confirm its path, and provide warning time to national command authorities. Minutes mattered. Even a short alert window could allow for retaliation or defensive measures. The Arctic environment shaped everything about the installation. Temperatures dropped far below freezing for much of the year. Darkness lasted for months during winter. Supply ships could reach the area only during limited seasonal windows when sea ice receded. Airlift supported the remainder of operations. Construction required specialized equipment capable of functioning in extreme cold. Personnel rotated through the base in defined tours because long-term assignment carried physical and psychological strain. Denmark maintained sovereignty over Greenland. After the Second World War, Copenhagen entered into defense agreements with Washington that allowed American forces to establish and operate facilities on the island. These arrangements were part of broader NATO cooperation. Publicly, Denmark stated that nuclear weapons would not be stationed on its territory during peacetime. That position existed alongside the strategic realities of alliance defense planning. For the United States, Thule was not a symbolic outpost. It was a component of an integrated detection network. Radar data from Greenland fed into command centers in North America. Operators tracked objects crossing the polar horizon and distinguished between test launches, satellites, and potential threats. The base also supported air operations, logistics flights, and communications infrastructure necessary to sustain high-latitude missions. The surrounding region offered little natural cover. Snow and ice dominated the landscape. The coastline opened into North Star Bay, which froze solid during winter months. Sea ice thickness varied, and weather conditions could change rapidly. Winds moved across open expanses without obstruction. Aircraft approaching the airfield relied on precise navigation due to limited visual references during periods of low light. By the late 1960s, Thule had become a permanent fixture in American strategic planning. Its radar capability contributed to deterrence by reducing uncertainty. If an adversary believed its missiles could not eliminate retaliation, it might reconsider launching them in the first place. The installation operated within a layered system of defenses: ground-based missile fields in the continental United States, strategic bombers, and submarine-launched ballistic missiles formed overlapping capabilities. Thule's role was not to deliver weapons, but to provide information. In nuclear strategy, information can determine survival. Personnel stationed there understood that their work connected to global stability. The base functioned around the clock, regardless of season. Radar operators monitored screens. Maintenance crews kept generators and support systems running. Air traffic controllers managed arrivals and departures in an environment where mechanical reliability was essential. On January 21, 1968, Thule remained what it had been designed to be: an early warning installation at the northern edge of Alliance territory. Its purpose was detection and communication. That day, however, it would become associated with something else entirely. Operation Chrome Dome was developed during a period when American defense planners questioned whether fixed bases could survive a surprise attack. By the late 1950s and early 1960s, the Soviet Union possessed long-range bombers and was developing intercontinental ballistic missiles. If those weapons struck U.S. airfields first, aircraft on the ground could be destroyed before they ever took off. The response was to remove some of that vulnerability by keeping bombers in the air. Under this policy, aircraft from Strategic Air Command flew continuous alert missions along predefined routes. These flights carried live nuclear weapons. Crews remained airborne for extended periods, refueled in mid-air, and returned only after completing their assigned patrol cycles. The system ensured that even if American bases were hit without warning, a portion of the strategic force would already be in motion and capable of reaching its targets. This approach required strict procedural discipline. Aircraft were loaded, sealed, and inspected before departure. Weapons were armed according to established safety protocols, but incorporated multiple safeguards intended to prevent unintended nuclear yield. Crew training emphasized checklist compliance and redundancy. Refueling tankers coordinated with bombers at designated points along their routes to extend endurance. The logic behind airborne alert was based on survivability. Deterrence depends on credible retaliation. If one side believes it can eliminate the other's forces in a single strike, stability weakens. Keeping bombers aloft complicated that calculation. An adversary would have to account for aircraft already outside the reach of immediate destruction. The operational burden was significant. B-52 crews operated in confined conditions for long hours. Arctic routes presented additional challenges, including limited diversion airfields and extreme weather. Navigation relied on inertial systems and periodic updates. Mechanical reliability was critical because options for emergency landing were limited in high latitudes. Within the broader framework, missions connected to Greenland had a specific purpose. Aircraft assigned to the Thule sector performed a function often referred to as hard head. These flights passed near the radar installation to confirm its operational status. If ground communications were disrupted, a bomber crew could visually verify the condition of the site and relay information through alternative channels. The arrangement tied airborne deterrence to early warning infrastructure. The aircraft involved in these missions were typically variants of the B-52 Stratofortress. By the late 1960s, the G model represented a mature configuration of the platform. It combined long range with the ability to carry multiple nuclear weapons internally. 8 jet engines provided the thrust required for heavy payloads over intercontinental distances. Carrying live weapons during routine patrol was accepted as part of the strategy. The weapons themselves were designed with layered safety mechanisms. Conventional high explosives within the bomb assembly were necessary to compress visible material in the event of detonation, but nuclear yield required precise sequencing. The engineering intent was to prevent a nuclear explosion unless the weapon completed a defined arming and firing process. Even so, airborne alert operations carried inherent risk. Aircraft accidents, though infrequent relative to total flight hours, were not impossible. Mechanical failures, weather, or human error could produce emergencies. The presence of nuclear weapons elevated the consequences of any crash. By the late 1960s, strategic doctrine had begun to diversify. Land-based intercontinental ballistic missiles were deployed in hardened silos across the United States. Ballistic missile submarines operated from patrol areas at sea, providing a concealed second strike capability. These developments reduced reliance on bombers as the sole guarantor of retaliation. However, airborne alert missions continued because they added another layer to the deterrent posture. Each sortie required coordination across multiple commands. Flight planners charted routes, tanker crews synchronized rendezvous times, maintenance teams ensured readiness before departure. Once airborne, crews followed precise timing to maintain separation from other alert aircraft operating in adjacent sectors. The mission that approached Thule on January 21, 1968, existed within this system. It was not an ad hoc flight. It was part of a standing operational structure designed to maintain constant readiness. The aircraft carried 4 nuclear weapons in accordance with its assigned role. The crew expected to complete its patrol and return to base as many others had done before. The structure itself did not anticipate a cabin fire. The aircraft assigned to the January 21 mission was a B-52G Stratofortress, serial number 58-0188. Its call sign that day was Hobo 28. The G model differed from earlier versions in fuel capacity and structural refinements that allowed extended range without constant dependence on tanker support. It was designed for endurance, not speed. 7 crew members were aboard. Standard complement included aircraft commander, co-pilot, radar navigator, electronic warfare officer, gunner, and an additional crew member positioned within the lower deck. The flight deck sat high above the fuselage with limited visibility outside forward windows. Below, narrow compartments housed avionics equipment, wiring bundles, and environmental systems. The aircraft had departed earlier as part of a scheduled alert sortie. Pre-flight procedures included weapon loading and verification. 4 nuclear weapons were secured in the bomb bay. The crew conducted inspections in accordance with Strategic Air Command protocols before departure. Nothing in those checks indicated a hazard. Flight conditions over the Arctic were stable. Exterior temperatures at altitude were far below freezing, but cabin systems maintained internal climate. Crew members wore standard flight gear appropriate for long-duration operations. Heating systems operated continuously to offset the extreme external environment. During the mission, additional seating cushions had been placed in the lower cabin area. Accounts from the official investigation described foam cushions positioned near a heating duct. The B-52's environmental control system circulated warm air through vents located along structural panels. The material of the cushions was not designed to withstand prolonged exposure to high heat at close range. At some point during cruise, a crew member detected the odor of smoke. Initial assessment did not reveal an obvious flame. Smoke accumulation in a pressurized aircraft can spread rapidly through ventilation pathways. Within minutes, haze began to obscure visibility inside the cockpit. The crew initiated standard fire response procedures. Circuit breakers were checked, electrical systems were monitored for anomalies. Attempts were made to locate the origin of the smoke source. However, the B-52's internal layout included multiple compartments separated by panels and wiring conduits, making precise identification difficult. As smoke density increased, instruments became harder to read. Communication between crew positions required raised voices. Fire extinguishers were deployed in suspected areas. The effort did not eliminate the source. Combustion within insulation or wiring bundles can persist behind structural panels even after surface suppression attempts. The aircraft commander evaluated available options. Returning immediately to base required maintaining control and visibility long enough to descend and approach in Arctic conditions. The nearest diversion fields were limited and not equipped for every contingency. Meanwhile, smoke inhalation risk increased. Systems began to degrade. Electrical malfunctions were reported. Some indicators flickered or failed. The crew donned oxygen masks to maintain breathable air. Even with masks, reduced visibility complicated checklist execution. At this stage, the decision threshold approached. Continuing flight risked incapacitation before landing. Remaining at altitude without resolving the fire increased the chance of structural damage. The commander chose to abandon the aircraft. Bailout procedures in a B-52G required coordination. Not all crew positions had identical ejection capabilities. Some stations required manual exit through hatches rather than upward ejection seats. The sequence had to account for aircraft attitude and altitude. The bomber descended toward lower altitude as crew members prepared to leave. One by one, they exited into Arctic air. Parachutes deployed against a background of snow and ice. Surface temperatures were extreme, and survival depended on rapid recovery by rescue teams from Thule. 6 crew members survived the descent and landing. 1 did not. The loss occurred during the bailout sequence. The circumstances were documented in subsequent investigation findings. Once the final crew member departed, Hobo 28 continued forward without pilot input. The aircraft's autopilot and trimmed flight condition allowed it to remain airborne briefly after abandonment. Without control inputs or fire suppression, the onboard blaze continued to compromise systems. The unmanned B-52 moved across the frozen surface of the North Star Bay. Its trajectory carried it several miles from the runway at Thule. Eventually, structural integrity failed, and the aircraft descended toward the ice below. Inside the bomb bay remained 4 nuclear weapons, still secured in place. No further crew action was possible. The abandoned aircraft descended in a shallow arc toward the frozen surface of North Star Bay. Without pilot control, aerodynamic stability degraded as structural damage from the internal fire progressed. Electrical systems failed in sequence. Control surfaces no longer responded in a coordinated manner. The bomber's mass and forward velocity carried it across the dark Arctic sky until it lost lift. Impact occurred on sea ice several miles from the runway complex at Thule. The B-52 struck at high speed. The fuselage fragmented immediately. Wings separated. Fuel ignited on contact, producing a wide debris field across the frozen surface. Inside the bomb bay, the 4 nuclear weapons remained attached at the moment of collision. Each device contained conventional high explosives designed to compress nuclear material in the event of proper detonation sequence. The crash provided violent force, but not the precise conditions required for a nuclear yield. However, the conventional explosives did detonate. The detonation of those high explosives tore the weapons apart. There was no nuclear explosion. There was no mushroom cloud. Instead, the blast dispersed weapon components and radioactive material across snow and ice. Fragments of metal, wiring, and bomb casings scattered outward from the point of impact. Burning aviation fuel spread contamination over a broad radius. The resulting fire consumed sections of the wreckage. Blackened ice marked the central impact zone. Debris embedded itself into the frozen surface. In sub-zero conditions, much of the material froze in place. The weapon safety mechanisms functioned as designed in one critical respect. The sequence necessary for nuclear detonation was not completed. A nuclear weapon requires specific arming signals and precise internal alignment before yield can occur. Those conditions were absent. The crash was catastrophic, but it did not produce a nuclear blast. The classification applied to this type of incident was a broken arrow. That term referred to accidents involving nuclear weapons that did not create a risk of nuclear war. It did not minimize severity. It identified the category. Radiological contamination became the immediate concern. Plutonium and other materials from the weapon assemblies were present in particulate form. Wind could transport fine particles across the ice surface. Snowfall could cover contaminated areas, complicating detection. Within hours, response teams at Thule began assessing the situation. Aircraft on the base conducted visual reconnaissance. Ground teams prepared to move onto the sea ice once conditions permitted. The location presented logistical challenges. Sea ice thickness varies, and heavy equipment must be deployed carefully to avoid breakthrough. The debris field extended across a broad area. Portions of the aircraft structure lay twisted and partially buried in snow. Sections of the wings and fuselage were identifiable, but much of the bomber was reduced to fragments. The bomb bay area had been obliterated by explosive force. Initial radiation surveys indicated measurable contamination. Monitoring equipment detected alpha radiation in the impact zone. Establishing the perimeter of the contaminated area became a priority. Markers were placed to define boundaries where protective gear would be required. Temperatures remained far below freezing. Wind conditions could change rapidly. Daylight hours were limited. Recovery personnel operated under both physical and radiological constraints. The fact that no nuclear yield occurred did not eliminate hazard. Plutonium poses risk when inhaled or ingested. Contaminated snow and ice required controlled handling to prevent further spread. The proximity to a major installation heightened urgency. Thule's runway, housing areas, and radar facilities could not be exposed to drifting radioactive particles. As reports moved through military channels, the scale of the event became clear. A nuclear-armed bomber had crashed within sight of a critical early warning base. The weapons had broken apart on impact. The Arctic surface now held scattered radioactive debris embedded in frozen terrain. Rescue crews recovered surviving airmen. Medical personnel treated injuries and evaluated exposure. Attention then shifted entirely to containment. The sea ice would not remain stable indefinitely. Seasonal change would eventually weaken its structure. Any material left unrecovered risked sinking into Arctic waters once thaw began. Time imposed a limit. The immediate objective was no longer flight safety or crew survival. It was control of a contaminated crash site in one of the most remote operating environments on the planet. Project Crested Ice began within days of the crash. The objective was defined in operational terms: locate contaminated material, remove it from the ice surface, and transport it out of Greenland under controlled conditions. The work required coordination between American military personnel and Danish authorities, since the incident occurred on Danish territory. The first phase focused on mapping the debris field. Radiation detection teams moved across the frozen surface using handheld instruments capable of identifying alpha contamination. Surveyors established grid lines to document readings at fixed intervals. Areas registered above background levels were flagged for removal operations. Wind patterns were tracked to estimate potential particle drift. Sea ice thickness was evaluated before heavy equipment deployment. Engineers measured load-bearing capacity to determine where bulldozers and transport vehicles could operate safely. Temporary routes were constructed across stable sections of ice to create access lanes between the base and the impact zone. Movement was restricted to designated paths to limit unnecessary surface disturbance. Personnel assigned to the contaminated area wore protective clothing and respiratory equipment. Procedures governed entry and exit from controlled zones. Decontamination stations were established near the perimeter to prevent radioactive material from being carried back to the main installation. Monitoring instruments were used to scan boots, gloves, and tools before personnel returned to non-restricted areas. Removal operations involved scraping surface snow and ice from contaminated grid sectors. Bulldozers pushed material into collection points, where it was loaded into lined containers. Crews were instructed to remove not only visible debris, but also surrounding snow that might contain microscopic particles. The emphasis was on over-collection rather than precision extraction. Fragments of aircraft structure were separated from snow where possible and packed for shipment. Larger wreckage components were cut into manageable sections. Items suspected of containing weapon material were handled under stricter controls and documented carefully. As work progressed, new snowfall periodically covered previously surveyed areas. This required repeated measurement passes to ensure contamination had not migrated beyond initial boundaries. Strong winds occasionally redistributed loose particles, forcing teams to expand the cleanup footprint. Collected material was transported to staging points at the base. From there, sealed containers were prepared for shipment to the United States. The logistics chains required coordination with maritime transport once seasonal access allowed movement by sea. All outbound material was documented, labeled, and accounted for prior to departure. Time pressure influenced decision-making. The Arctic winter provided a stable platform while sea ice remained solid. As spring approached, rising temperatures would weaken structural integrity. Engineers calculated projected thaw times to determine how long heavy operations could continue safely. Completion before breakup became a planning priority. In addition to surface removal, teams searched for weapon components. Recovery of critical parts was necessary for accountability and technical evaluation. Divers were later assigned to examine areas where debris may have penetrated through ice fractures into underlying water. These underwater efforts required specialized equipment suited to extreme cold. By late summer, the main removal phase concluded. Reports indicated that large volumes of snow, ice, and debris had been collected and transported. Monitoring readings within the cleared zone were reduced significantly compared to initial measurements. On September 13, 1968, the operation was formally declared complete. Official assessments at the time stated that the contaminated material accessible on the surface had been removed to the extent feasible under existing conditions. Documentation summarized grid surveys, container counts, and shipment records. The base resumed normal operational posture following the conclusion of the cleanup phase. The environment itself preserved much of the worksite's stability. Low temperatures slowed melt and limited biological interaction with remaining material. However, the operation did not involve excavation of the entire seafloor beneath the crash location. The scope was defined by what could be located and retrieved within the operational window. Project Crested Ice represented a large-scale logistical effort conducted under environmental and radiological constraints. It required heavy equipment, protective procedures, and coordination between two governments. The objective was containment and removal, not long-term environmental study. When the final teams withdrew from the ice, the visible wreckage had been cleared. The grid markers were removed. Temporary access routes were dismantled or allowed to blend back into the frozen surface. Documentation moved into archives, and personnel rotated out of Greenland. The crash occurred on territory governed by the Kingdom of Denmark. That fact shaped the political response immediately. Denmark had publicly stated that nuclear weapons would not be stationed on its soil during peacetime. Greenland, though geographically distant from Copenhagen, fell under that policy framework. The presence of an aircraft carrying 4 nuclear weapons near Thule introduced tension between stated policy and alliance practice. In the days following the crash, official statements focused on the accident itself and the ongoing recovery effort. The emphasis was placed on the absence of a nuclear detonation and on the cooperative cleanup operation underway. Technical explanations were limited in scope. Details about airborne alert operations were not widely discussed in public briefings. Within Denmark, questions arose regarding the extent of American nuclear activity connected to Greenland. Parliamentary inquiries sought clarification about whether Danish authorities had prior knowledge of nuclear-armed flights in the region. The issue was politically sensitive because it intersected with national sovereignty and alliance obligations. The government in Copenhagen faced competing pressures. Denmark was a member of NATO and relied on collective defense guarantees. At the same time, domestic political sentiment included strong support for nuclear restraint. Managing both positions required careful language. Over time, additional documentation emerged. Declassified materials and investigative reporting in later decades suggested that American strategic planning involving Greenland had been more extensive than initially described in public forums. These revelations renewed debate within Denmark about transparency and decision-making during the Cold War. The crash became a reference point in broader discussions about the balance between security cooperation and national policy. Critics argued that Danish leaders had not fully informed the public about the scope of U.S. military operations in Greenland. Defenders countered that alliance defense arrangements required confidentiality during a period of heightened global tension. The United States maintained that airborne alert missions were part of a deterrent structure designed to prevent conflict. American officials emphasized that the incident had not produced a nuclear explosion and that cleanup operations had been conducted jointly with Danish participation. The position presented the accident as an operational failure within a larger defensive framework. Political reaction evolved over decades rather than weeks. In the 1990s, renewed scrutiny followed the release of archival material. Public discussions expanded beyond the immediate crash to examine the broader relationship between Denmark and the United States during the Cold War. Parliamentary reviews revisited prior government statements and assessed whether they accurately reflected the realities of the period. The diplomatic consequences did not result in the closure of the base. Thule Air Base continued to operate under bilateral agreements. However, the episode altered the tone of public debate surrounding its presence. Nuclear issues remain part of that dialogue. For American policymakers, the incident highlighted the political exposure that accompanied strategic operations conducted on Allied territory. Even when safety mechanisms functioned as intended, the mere presence of nuclear weapons could generate domestic controversy abroad. The crash, therefore, carried two dimensions: operational and political. The operational aspect concluded with the removal of debris from the ice. The political aspect extended into parliamentary chambers and public discourse, where questions of consent, disclosure, and alliance management persisted long after the Arctic winter of 1968 had passed. The dispute did not overturn the alliance. It did, however, leave a permanent entry in the record of U.S.-Danish relations. After Project Crested Ice concluded, attention gradually shifted from containment to long-term health concerns. Danish civilian workers had participated in survey, removal, and transport operations during the cleanup phase. Some later reported medical conditions that they believed were linked to radiation exposure at the crash site. The primary allegation centered on cancer incidents. Former workers argued that protective measures in 1968 were insufficient and that monitoring procedures did not fully account for inhalation or ingestion risk. They maintained that exposure during snow removal and debris handling contributed to later illness. Government authorities in Denmark and the United States conducted reviews over subsequent years. These assessments examined radiation measurements recorded during the cleanup, protective protocols used at the time, and estimated dose calculations for personnel operating within contaminated zones. Official findings generally concluded that exposure levels were below thresholds associated with significant long-term health effects. The disagreement persisted because dose reconstruction decades after an event is inherently imprecise. Records documented contamination levels in grid sectors, but individual exposure can vary based on duration, proximity, and adherence to protective procedures. Workers who developed serious illness questioned whether archived measurements reflected actual conditions on the ice. Legal efforts followed. Groups representing affected individuals sought compensation or formal recognition of potential harm. Court proceedings and administrative reviews evaluated claims against available documentation. Outcomes varied, and not all claims resulted in awards. The issue also carried symbolic weight. For many former participants, the question extended beyond medical causation. It involved acknowledgement of their role in managing a nuclear accident under extreme environmental conditions. The cleanup had required long hours and cold temperatures, with limited margin for procedural error. Those who served believed that their contribution warranted consideration, even if direct causation could not be conclusively established. Scientific panels continued to reference original monitoring data. Reports emphasized that the weapons did not produce a nuclear yield and that contamination was localized primarily within the defined crash perimeter. Officials argued that containment and removal operations reduced the probability of sustained exposure outside restricted zones. Critics responded that official dose models might underestimate internal exposure pathways, particularly in circumstances involving fine particulate matter and windy conditions. The debate therefore focused less on whether contamination existed and more on how much of it had entered the bodies of those working nearby. Decades after the crash, the health dispute remains part of the historical record. It represents a separate dimension from the operational and diplomatic aspects already examined. The accident introduced radioactive material into an Arctic environment. Cleanup crews removed visible debris. The long-term health interpretation of that exposure continues to be evaluated through competing claims and official review. In the weeks following the crash, airborne nuclear alert missions were terminated. Operation Chrome Dome had operated for years as a safeguard against a surprise strike, but the Thule accident demonstrated the risk inherent in keeping armed bombers in continuous flight. The policy ended shortly after January 1968. Strategic emphasis shifted further toward land-based intercontinental ballistic missiles and submarine-launched ballistic missiles. Fixed missile silos, hardened against attack, provided rapid response capability. Ballistic missile submarines operating beneath the ocean surface offered concealment and survivability. Together, these systems reduced reliance on aircraft remaining airborne with live weapons. Strategic bombers did not disappear from the deterrent structure. They continued to operate on ground alert and retained the ability to deploy when required. The difference was procedural. Continuous airborne patrol carrying nuclear weapons became a practice of the past. The base in Greenland remained active. Thule Air Base continued to support early warning and space surveillance missions in the decades that followed. In 2023, it was renamed B2Feek Space Base, reflecting organizational changes within the United States Space Force. The events of January 21, 1968, did not alter the broader framework of deterrence. They did, however, influence how risk was managed within that framework. Airborne nuclear patrols ended. The Arctic installation remained. Strategic doctrine adapted to incorporate lessons drawn from a single aircraft that did not return from its mission. On January 21, 1968, a strategic bomber was lost to an onboard fire while carrying 4 nuclear weapons. The impact scattered radioactive debris across Arctic sea ice. Recovery teams removed contaminated material under severe conditions. Parliamentary debate followed in Denmark. Airborne patrol procedures were revised. Thule remained operational. The radar arrays continued scanning the northern sky. Strategic systems evolved in the years that followed. The aircraft did not return from its mission. The consequences extended far beyond the wreckage. I'm Dave. I appreciate you watching. Please subscribe, like, comment, and share. And until next time, stand tall.
Oh, Dave.